All right, thanks for coming. This is AWR1Page, sanity checking, time instrumentation in AWR reports. It's a mouthful. We okay? Okay, what's happening here, Tim? Wow. A few acknowledgements. Sans Yuri Shaft, who I'll acknowledge personally right now. Kevin and Connor basically sort of provided the motivation for the AWR1Page. AWR1Page is just a report, right? It's a giant awk script that consumes an AWR report and spits out one page. But I'm getting ahead of myself. Graham for mentorship, advice, and insight, and that goes also for Yuri Shaft. And then after I thought I had the thing developed, I solicited other Oak Table members for AWR reports just for testing purposes. And these guys kindly provided test cases which exposed numerous bugs. So that's why you want such things. So I'll just talk a little bit about the motivation, which is basically AWR reports are massive and confusing. I'll talk a little bit about the model of time in the database and the instrumentation for that. Then we'll say, a little discussion about when the models and the measures don't match, which is really the purpose of the talk here, which is inconsistent instrumentation. The concept and design of AWR1Page, then basically the two case studies presented by Kevin and Connor. And then just some final thoughts. So, motivation, confounding AWR reports. Anybody used an AWR report before? Have you ever read it start to finish? No, it's ridiculously big. It's just a giant dump of numbers. It resembles, it's not unlike the old core dumps that as COBOL programmers we used to have to peruse once in a while. So I basically was presented first with a question from Kevin Clausen about why numbers didn't seem to add up on an AWR report that he was looking at. And, that resulted, it took me a while. It took me like a week, really, not like a whole week, 40 hours, but it took me quite a while, numerous trips through the AWR report to basically suss out that there was a CPU underweight problem. In other words, a wait event was accumulating a significant amount of CPU, and that was basically an instrumentation issue that can throw numbers off. So the talk that resulted was called AWR Ambiguity, and basically it was about that one report and that one issue. A year later, Connor came up with another confusing AWR report. And having remembered the pain that I endured just trying to answer Kevin's question, that's when I said, okay, we got to have some automation here, right? Because basically what I was doing with in Kevin's case was going through the entire report, highlighting a line here, a line there, page 30, page 47, page 12, page 18, then going through the whole thing and writing the numbers down on a yellow pad with labels telling me what they were, and then I could start thinking about it. So basically that whole go through with the yellow paper and with the yellow pen and highlight and transcribe, that's basically what AWR1Page does. So it's no easier to reason about the problems. It's just that you got all the data in front of you. And so it's much easier from that point of view. So it's a mentally excruciating issue to try and take on. So AWR Ambiguity, this was sort of the takeaway slide that people kind of liked, which was basically a list of symptoms that you might see and the possible instrumentation issues that could be responsible. So you might see that database CPU, time model database CPU, significantly larger than ASH CPU. And this was basically Kevin's problem. There was CPU being used within the wait. So it was being counted in the time model, but it was also in ASH. In ASH, the time was looked at as wait time, and in time model, it was being counted as both CPU and wait time. ASH CPU much greater than DB CPU. Well, if the system is CPU bound or CPU saturated more correctly, that can be the issue there. So that's not really an instrumentation issue as much as you know, sort of an issue altogether. And the reason for that is because the ASH will include the run queue time as being on CPU, whereas time model only measures real CPU cycles used. So ASH will over-report. DB time is much greater than DB CPU plus event wait time, and the system's not CPU bound. Well, this could be an uninstrumented wait because it's in a call, so therefore it's part of DB time. It's not in a wait. It's not on CPU, so it shows up. Well, it'll show up in ASH as on CPU, but Yuri, you can help me with this one. I'm losing the thought here. Anyway, final one, the ASH DB time, much less than time model DB time. This could be double counted DB time, which was an early bug with the job queue. Or ASH drop samples, which I don't know if we have any examples of that, but ASH can drop samples under, in cases where the mechanism fails to get a consistent snapshot of the session in subsequent grabs. In other words, the session is so active that it basically confounds the ASH mechanism, and ASH will actually drop samples. It can. I don't know that it's ever been reported, but as of around 11.2, I think, it started being counted. So at least you can know whether it's happened or not now. There's actually in $v ASH info, there's a column for drop sample count. Okay, so this is the basic model of time spent in an Oracle database, right? So the model is Oracle time, and I'm saying Oracle time, not DB time, because I'm including backgrounds here. But basically, any time spent by processes in Oracle are either on CPU or in wait. In other words, the total time is the sum of the CPU time plus the wait time. And the assumption is there's really no overlap. So basically, we really only think about active sessions, right? So they're in a database call, and they're either on CPU or in wait. If they're connected to the database but idle, they're not very interesting. They're not contributing to any issues, and they're not accumulating time, real time, in the database. And we have multiple measures for various of these these time components. So time model tends to measure total Oracle time as well as CPU time. We have event instrumentation, which will measure wait time. And we have ASH, which we use to estimate both CPU and wait time. So this is basically some of the instrumentation sources we're talking about. So the wait model or the event model, $v system event, time model, $v time model at the session level. There's also SES time model. OS timing, $OS stat. So it's always good to have information about the enclosing environment outside of an Oracle database, or that subsumes an Oracle database. And then we have ASH, Active Session History. Hopefully everyone is familiar with these instrumentation sources. Oh, just a note here. Stop using $sysstat CPU used by this session and move on to time model CPU. So instrumentation essentials, right? Run queue time distorts everything. Wait events get expanded. Time, latencies for wait events get expanded. ASH and time model don't agree on CPU, various issues. Time model, so this is sort of how these things are measured. So elapsed time in time model, or DB time in time model, is basically, when the call started, when the call ended, minus any idle time accumulated during the call, okay? So, one of the things to know about that is you usually trust database time, the call start and the call end points pretty well, right? In other words, that big boundary of how much time spent in the database is usually a pretty trustable number. And where issues tend to accumulate is, in the subtracting of idle wait time or in the measuring of wait time. ASH on CPU is not a measured value, it's a calculated value, okay? So basically, if a session is active in a database call and it's not in a wait event, then ASH says, oh, it's active, I mean, it's on CPU. So it's not observed to be on CPU, it's deduced to be on CPU. Time model CPU, on the other hand, is measured. So time model CPU does not accumulate run queue time. Time model CPU is basically about how much actual instruction time was used. OSStat is a source for external operating system information, in particular about CPU and also about run queue. But the reliability of that information can be somewhat very platform dependent. So there can be sort of OS specific issues that accrue in OSStat. And smaller call latencies increase distortion. What I mean by that is basically the run queue issue. So if you're basically in a latch wait, which would have a very small expected latency, then if you actually have to sit on the run queue in order to finish the wait event, that time on the run queue could dominate the actual wait time for the latch, okay? So the distortion is much larger than, say, in the case of perhaps an I/O wait event, which would have a longer expected latency. So another thing to know is basically this business about average active sessions. So if you've been here all day, you've heard me talk about average active sessions, you've heard Kyle talk about average active sessions. So it's really the essential Oracle performance metric, kind of King Kong among performance metrics. So the definition is basically instrumentation time, and by that I mean time spent in the database produced by whatever instrumentation you're concerned with, divided by elapsed time. So time spent in the database over some time interval divided by the length of that time interval. And then another useful thing to do, sort of further normalizing, for purposes of, let's say, comparing big systems to small systems, or would be computing average active sessions per core. Okay, so that would just be normalizing on a per core basis. So I did sort of the first talk about average active sessions in RMUG of 2007. Still kind of saying very much the same things, but the concept is no less important today than it was then. Okay, so AWR reports are massive. Time data is scattered about throughout the report, so it's difficult to kind of compare and reason about the time data in AWR. And the units can vary. So breakdowns are inconsistent, not normalized. So it's a little bit, comparing things for sanity checks is not so easy. And so doing these kind of consistency checks, seeing whether ASH and time model and OSStat line up or don't line up, is very labor intensive and error prone, as I found out when I was trying to diagnose Kevin's issue. So the cognitive load is just basically huge. And it's really, very few people would have the patience to engage in the activity that I did for Kevin, because it was a real pain in the ass. And you tend to want to trust the instrumentation, right? And so immediately, he didn't trust it. He knew enough to say, hey, these things don't add up. But he wasn't even about to try and, kind of figure out what was going on. Because you have to kind of understand what things should add up. You have to understand kind of how the instrumentation works, and then be able to reason about, okay, this is probably the part that's telling me not the truth, and this is probably the part that's telling me closer to the truth. So it's actually a difficult exercise. But the AWR report doesn't make it any easier. That's the whole point of this little talk. So we talked about this already, run queue time. You really want to check your CPU situation first. This basically goes for reading a normally unproblematic AWR report. What your CPU story is with respect to performance is always the most important thing to check. Now, some of the other things, we talked about this already. If you're accumulating CPU underweight, then your time model weight will be much less than sort of your event weight. Time model weight is basically total DB time minus time model CPU. So it's a derived value in the sense that ASH CPU is derived. There's basically some misleading OS CPU reporting under, especially under IBM AIX with symmetric, with SMT enabled. And there we can find things like ASH CPU being much greater than time model CPU. The sort of ASH CPU greater than time model CPU is a common symptom with different possible causes. So a lot of times that's going to be the symptom, and you're going to have to wig out which of the causes there are. Again, double counted DB time was an early 10.1 bug where job queue processes would, as they ran and accumulated DB time, they would post that incrementally. But then when the job queue finished, it would post all its DB time again. So it was double counted and could throw things way off. But that's been gone for a long time. What version is Oracle up to now? I stopped around 12.1, 12.2, I guess. 18? 6 versions since I worked at Oracle? That's impressive, 2 years. More sources of inconsistency. Uninstrumented wait events. Yuri, are there any more of these? Probably, okay. So in the case of an uninstrumented wait event, ASH will show being on CPU because it knows that the session is active in the database and yet it's not in a wait event. So it must, again, it's derived, so ASH thinks it's on CPU. So ASH CPU, again, will be much larger than time model CPU. That's sort of the, let's see, there's 1 of those, 2 of those, 3 of those. So that's a common symptom, right? So there's a lot of causes for that symptom. If there's an active event classified as idle, Yuri, any more of these? Are you still arguing about PQ events? So everybody's underreported, basically. So it's a little hard to suss that one out, right? Dropped ASH samples, again, I made reference to this. These are more arcane, esoteric symptoms, dropped ASH samples. The actual interval size? Oh, okay, nice. Yeah, you can sum up the actual thing. That's good to know. I actually investigated that in an earlier thing by just diffing successive sample times. It was kind of interesting. We'll talk about it now. But and then idle events that are using CPU, of course, the CPU time will accumulate in time model, but since they're idle, that time will be subtracted from the total DB time. So that's a real kind of screw up there. Okay, so always check CPU first. I said this already. OS stat, average active sessions busy per core is a nice thing to compute, which AWR1Page does. OS stat again, load average per core, not exactly the same thing. Should be close though. OS stat, OS CPU weight. So basically computing this is sort of a run queue. So this is a number I don't think is consistently reported, if I'm right, across platforms, but it may be very useful because it's kind of the only number you can actually look at and get a sense for, really how much run queue time has been accumulated. That's basically what it's supposed to be. Time model, it's useful to compute CPU average active sessions per core. And then CPU threads per core. In other words, the hyperthreading factor is always something that's very important to keep in mind. So some consistency checks. Basically, are you possibly CPU saturated? So is your core utilization, your per core utilization, greater than 1? Now, if it is greater than 1, it doesn't mean that the wheels are falling off, but there's a good chance of it. Okay, so some applications can get benefit of hyperthreading such that core utilization can exceed 1 or 100%. But like I said earlier in Kyle's talk, if that's the case for you, just consider yourself lucky. I certainly would worry about it. How does time model compare with ASH overall in terms of DB time? And then how do all the CPU numbers line up, especially time model and ASH, but also with the OS, assuming that it's a dedicated host and there should be nothing much more running than the Oracle database. These things should approximately line up. How does the time model average active sessions or total DB time compare with time model CPU plus event weights, right? In other words, measured CPU plus measured weight, how does that compare to total measured time? And then finally here we have how does time model weight compare to ASH weight compared to event weight? So these are kind of things that you want to sort of compare to each other. And if you look at an AWR report, this is the stuff that's buried all over the place that you want to sort of surface together so you can kind of think about these things. So let's just look at this again. So if the Oracle time is much less than the measured CPU, time model CPU plus event wait time, right? It's kind of like that top diagram. Well, that's not possible, right? So how is that possible? Well, basically, the CPU is being measured, so we trust that. The wait time is being measured, we trust that, but it's possible to have accumulated CPU while you're in a wait event. And if that's the case, it's going to be counted under both, right? So CPU under wait counts as both CPU and wait, and that's basically what's happening usually when you observe this situation. So alternatively, if the total time exceeds the sum of the CPU, the measured CPU, so the measured total time exceeds the sum of the measured CPU time plus the measured wait time, well then somebody's undercounted, probably. Again, we pretty much trust the total time because the start and the end of the call are pretty easy places to take a measurement. In other words, not a lot that can go wrong there. It's basically accounting for things inside that can be problematic. So on the wait side, maybe the wait is being undercounted. Maybe there's an uninstrumented wait. On the CPU side, maybe CPU is being undercounted. AIX being one culprit for that, which is basically misreporting CPU, or at least reporting CPU. It's hard to say misreporting. I mean, they're doing what they're doing, but it's certainly not adding up from an Oracle point of view. I'm not going to talk a lot about this. I still don't really understand it. According to Graham, it's just broken. Graham, that was a 2-year-old quote. Are you going to stand by that quote? It's still broken. Okay. A couple of blog references here. A couple of the Oak Table guys have done some investigation and exposition of this issue. But basically, Graham, you can say anything here if you want. But you know, if you got SMT4 under AIX, you might want to increase the reported CPU. When you say reported, you mean the Oracle reported CPU, right? So DB CPU is going to be short under AIX, and you know, just inflated by 50%, and you're probably a lot closer to the truth. 100%? Okay. So that's good to know, right? I mean, you're basically being told you're using, you know, 2 seconds of CPU, and you're using 4 or 8 or whatever. 4. Or, yeah. Clever of them. Right. Yeah, it's just yeah, they're misreporting, or they're at least, you know, they're reporting what they want to report, not what you want to actually hear. Okay, so let's move along. Let's see how much time I got. I think I'm using up too much time. So the objectives are basically, you know, reduce the cognitive load for doing these kind of consistency checks, which are painful even if you've got it all on one page, right? And then also facilitate comparative assessment of systems, you know, the size of the system and the busyness of the system. So you know, I want to basically be able to take AWR1Page from system A and system B and have things normalized in such a way that I can make some useful comparisons between the two, even if one is, very much larger than the other in some fundamental way. And do it all in one page, right? So AWR is 50 pages or 100 pages. So the goal is get it down to one page. So here are basically the sources where in the AWR report that are used to generate the one page. So OS stat, time model stats, foreground weight class. So these are little snippets from the AWG program, right? $0 matches operating system stats. It basically just finds the header of each section that I want to find and then enters a section-specific function that parses out the data and creates little arrays with the data in it, and then at the end does a report. And I also collect a couple of other singletons, like total elapsed time of the AWR report, how many cores are being reported, CPUs, so you can get the hyper-threading factor, and what platform obviously it's on, because it's kind of important to know if you're on AIX, and CPU is immediately suspect. So this was sort of the basic idea. Sort of the first thing I scratched out on paper was, okay, on the left column, that'll be sort of the labels for the info. And then each of the different data sources will have a column unto itself. And then we'll kind of organize the data sort of, host down to Oracle, and then maybe some miscellaneous. And then within, where there's breakdowns, we'll have the breakdown. So, host CPU can be broken down between sys and user time. And Oracle CPU, Oracle DB time, so Oracle total here, this would be total DB time, and that can be broken down into CPU and weight, right? So that's sort of just the basic idea. And then fill in the blanks where they're available. So where, OS stat is obviously going to be reporting this kind of stuff. Time model and ASH can both make reports about these data here. So we can compare time model to ASH if they appear next to each other as in the design here. So you want to compare rows across for equality. Wherever the same measure is produced by different instrumentation sources, you want to just see that, on a line next to each other. And then columns should add up sort of hierarchically. So that's kind of the idea. So then I said, okay, well, let me see, what do I got? That's when I got into the AWR report and started saying, okay, I got this, 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 this. So this is sort of the next level of design for the report. And then I did a design mock-up, so that's what this is here. And it's a little bit, it's probably a little bit hard to read. It doesn't look too bad. But basically, this, again, I just did this in like Excel or something. This is still just, at the level of kind of a mock-up and not a real report. But you can see here, I wanted to surface the number of cores, number of CPUs, number of threads, total elapsed time. So a couple of design notes there. So average active sessions is also average active processes. So if you're talking about host CPU, it's kind of more, sessions is kind of an inside Oracle concept. So you can compute the same numbers, total time divided by elapsed time for host CPU, and you might want to call it average active processes or threads or cores or whatever, but I just call it average active sessions, altogether. All the numbers on this sparse matrix in the design are in average active sessions. Okay, so we normalize everything to average active sessions. And again, things that you should be able to compare for equality should appear on the same line. And then we use indentation and vertical position to sort of represent the hierarchy of a total divided down into subtotals. And then some cells have this convention where there's a bracket and two numbers separated by a colon. And so the first number is the average active sessions, and the second number is the core normalized average active session. So for instance, I wanted just one place to go to see on a core normalized basis, was I CPU saturated, right? So if that number is close to 1, it's very possible that I'm CPU saturated. And there's just one place to go to answer that question. No in the head computation. So here's the actual output. I'm not a Perl guy like Jared, but basically I wrote an awk program because I was being presented with text AWR reports. And then of course, once I got the thing working, somebody said, well, here's an HTML report. I'm like, my awk program is not going to swallow your HTML report. And I'm not about to write it, you know, I'm not about to write another version of it. So I know a guy, Graham here, he wants to learn Python. I'm trying to recruit him to do the Python version that'll suck in the HTML report and do the same thing. So, but basically this is what it looks like. Now it's kind of inscrutable. And I have to say, I did this presentation 2 years ago, and then when, you know, I didn't really change it, but when I was going through the presentation saying, oh man, how do I read this thing again? But at least I didn't have to deal with like 50 pages of stuff, right? So it basically just goes and gathers the stuff up. So again, you can see this thing on. So, right, Ash, time out. Well, I think I have a build here, right? So yeah, basically here's the sections vertically, right? So host, Oracle, and then miscellaneous, some miscellaneous stuff that I just wanted to put in there. But mostly we're talking about host and Oracle. And then, you know, OS stat, so then the, you know, the vertical sections are for each of the different instrumentation sources. So only Ash data will appear in this column, only event weight data will appear, you know, only OS stat will appear here. But you can see OS stat actually produces some Oracle relevant information in the form of resource manager, CPU weight, which you don't always see, but you know, if it's there, you'll see it. So again, you compare across for equality, so that's not a bad matchup. Again, Ash is estimated, time model is measured, so you're not looking for, you know, hundredth of a active session accuracy when you're comparing across like this. So, you know, 0.14, 0.13 on a per core basis, not a problem. Again, here's the number you look at for CPU saturation, right? This is OS CPU on a core normalized basis, 0.17. Not a CPU saturated system, one number. Ah, there it is, core utilization. Okay, so how are we doing on time? Maybe we'll just go through the first one. Oh, 17 minutes. I must have sped up. So again, I talked about these case studies. So anybody know Kevin Clausen? Yeah, he's kind of, you know, it's kind of hard not to know about Kevin, right? So he presented a case study, and of course, you know, he was benchmarking Oracle I/O, big surprise there, right? So being a slob, so-called, right? So here's his AWR1Page. And so we can see it's a decent sized Linux system, right? How many cores? 36. It's Linux. We like Linux because Linux tends to report CPU accurately. So we think that things like time model CPU will be well reported, which is a good thing. Interesting, we have the interesting here, the elapsed time of the AWR report is 2 minutes. Anybody running 2-minute AWR reports? That's a regular practice in your shop? Every 2 minutes, snapshot in AWR? Now, Kevin's a benchmarking guy, right? It probably takes 10 seconds for his framework to get up and start pounding the system, so 2 minutes is more than enough time to do whatever he wants to do, right? And he's impatient, so why should he wait longer than 2 minutes? Let's see here. Okay, so again, I said it was a Linux system, and we like Linux because we think CPU is generally reported very, very good way for us. So we're gonna bias towards trusting these CPU numbers, and in particular, we don't think there's any issue with CPU saturation, right? We're at 17% CPU on a per core basis. So on a per thread basis, that would be what, half that. What else? Oh, so non-trivial I/O weight, right? So total average active sessions about 6, and fully half of that is on I/O weight. Well, okay, we know Kevin, that's not a big surprise, but if there's an issue, you know, it's more than likely going to involve I/O, right? If there's a instrumentation issue. So again, because it's Linux, we like CPU reporting on Linux, we're going to say, let's trust time model CPU. So let's call that the bedrock. We're going to basically compare other numbers to that, okay? And in particular, you know, we like this number of 5 average active sessions for total DB time and 2 average active sessions on CPU, okay? Well, let's take a look over here. 2.5, oh, issue right there, right? Time model CPU, much greater than ASH CPU. We don't like that number. We don't like those numbers. So basically, what's going on here? Well, we've got to get up to 5. We trust this number, right? 2, 5. So we've got 3 average active sessions to account for in the database. I/O weight is reporting 4.32, right? Well, there's only 3 that we got to spare. So let's give them all to I/O weight and say there's actually 1 average active session on CPU inside this weight event, and that's what's going on. Okay, so by figuring out what to trust and how to backfill what to not trust and account for it. So basically, so there's 1 average active session on CPU under I/O weight, and there's only 2 average active sessions of CPU being measured. So fully half of the CPU being consumed during this benchmark is under the I/O weight events. And, you know, I don't think Kevin would dispute that. So, you know, he's probably fooling around with some kind of advanced I/O subsystem that's, you know, under, you know, Oracle issues a wait event call, and then all kinds of CPU gets used by the foreground underneath the wait event. Once Oracle thinks it's in a wait event, whatever happens underneath there, it still thinks it's in a wait event until that wait event gets posted as being over. So if there's a lot of CPU being consumed in there, it's not going, hey man, you're using CPU, you're supposed to be in a wait. No, it's just going to accumulate CPU in time model and also be considered in a wait time. So again, it's CPU underweight throws our model of time in the database off. Okay, case study 2 from Connor McDonald. So this was an Ask Tom question. Everybody knows Connor's the new Ask Tom, right? Well, Connor and others. So there was a confusing AWR report, and this is the one that drove me over the edge. You know, Kevin's, you know, I wigged Kevin's thing out, and I said, okay, for the trouble I put into it, I got a little presentation out of it, and I did this at Oak Table World a couple years ago. But when Connor came up with something similar but different, it was like, Jesus, I can't go through that again. And so automation was required. So here's his report. So first red flag, AIX, okay? We already know we're not gonna believe CPU, or we're at least gonna, you know, think about it very, very carefully. Unlike the previous report where, you know, it was on Linux, we like Linux, it seems to report well, so we like it. So it's a small system, 2 cores, but SMT4, okay? What's the inflation factor, Graham? 50%, okay, so there you go. So it's a small system with lots of multi-threading going on. So is it CPU bound? Okay, so the per core number is 0.57. Well, you know, you wouldn't normally think it was CPU saturated, but again, it's on AIX. So it's probably lying to us in the first place, right? So that number, again, add half to that, and you're at what, 0.8. Now you're talking possible issues, right? And more than that, these numbers are really looking squirrely, right? The load average is 4 average active sessions, but CPU busy is only a bit more than 1, okay? And OS CPU weight is basically reporting almost the entire load average. So these numbers just don't add up, right? You know, this should be the total of, you know, I/O weight plus, well, I guess it is, right? 0.07, 4.06. So basically, this is kind of telling us you know, nothing in the load average is really CPU, and then this thing is actually telling us, well, you know, at least 25% of the load average. So this stuff is just not adding up, right? This plus this should equal that, right? Again, we add up to a higher level, and it's just not adding up. So, you know, we're already kind of confused here. Okay, so let's look at time model and ASH. Well, in terms of total dB time, time model and ASH are, you know, they're kind of agreeing. 0.62, 0.72, you know, that's reasonably close enough. And this is with respect to weights. ASH and weight class, ASH and event weights are more or less lining up, right? 0.06, 0.05. So these things seem to agree about what's going on. So, you know, that's kind of a good sign in a certain sense. So what don't we believe? Okay, so time model and ASH, you know, ASH, this bottom one, these two guys agree, right? So let's just say this guy we don't like, okay? These two are in agreement, we'll throw him out. And we'll say he really should be 0.06 to line up with these guys. And we don't like this one, similarly, right? So this should really be 0.56, right? So now we, you know, 0.62, we need to get to 0.62. Well, how do we get to 0.62? Well, we get there from 0.06 and 0.56. Now we got number. This number plus this number should equal this number, but we don't believe either of these two numbers. We do believe this one, so this is what we think is the truth in this case. So it's basically, you know, a case of the CPU being reported problematically. And here it looks like the inflation factor is quite a bit more. So again, the conclusion here is, you know, dB time is greater than dB CPU plus weight. So it's either run queue or CPU being underreported, or quite possibly both in this case. And that wasn't easy to figure out, you know, because we were kind of being lied to. And, you know, and this is really, you know, you can really kind of get the confusion right here. You know, these numbers are just not adding up in the way they should. Okay, so basically, you know, it works, kind of. I mean, you still have to be pretty savvy about the instrumentation in order to wig out the issues, but it kind of makes, you know, the impossible possible, right? I mean, scrolling through a 50-page AWR report just to pluck out little tidbits of time information, you know, only a guy as dedicated and perhaps stupid as me would actually endeavor to do that, right? Some things I'd like to do with this, basically rewrite it into Python, because, you know, a 700-line awk script is kind of like, you know, it should be illegal. It's fragile. I mean, it works. And it actually stood the test of multiple test cases. Now, you know, it's very possible that AWR report has been changed in current releases. It's good up to 12.2, I think. I think I tested on 12.2s. But, you know, accepting the HTML version would be nice. And again, you know, Graham, that can be your first Python project. I think I highly encourage that. I really wanted to do like an AWS Lambda service where, you know, you could, you know, upload your AWR report, and I'd email you the one page, and they'd say, I can't make sense out of this fucking thing. I'd say, it's only $1,000 an hour to hire my consulting services. And that may still be coming. Your second project, Graham, can be an AWR Lambda. And then the other thing is basically doing a SQL version, right? So let's write a SQL version that goes directly at the instrumentation sources. One of the problems with the AWR report was, you know, there's very little ASH information in there. I mean, I was really scratching to get the ASH information. Whereas if we were connected to an Oracle database, we could really go after real ASH data and do a much more thorough job, and also have access, you know, direct access to all the instrumentation sources. So, and Yuri, this is for you. These kind of sanity checks should be in regression tests, or at least in Adam. You know, Adam should do a sanity check on the instrumentation before he starts drawing conclusions. Maybe he does. Anyway, and the other thing to report that's new is basically I've created an open GitHub repository multiple repositories for my little projects that I've done presentations on over the years. And this is one of the ones that I hope somebody will actually contribute to, like, you know, doing the HTML version and maybe even some of the other stuff. So food for thought, please contribute. There's me at the Pumpkin Festival earlier this month. Reference to the GitHub page and my LinkedIn profile.